Welcome everybody to those of you joining us on YouTube. So right now we have calculus. So this is April 22nd, and we are in section 3.2 in our calculus textbook. So we'll finish that up today looking at families of functions. So when we say a family of functions, what we mean is we have a collection of functions that behave similarly. So if I looked at a definition like this, f of x equals ax plus x squared, these functions all have a similar formula, and they're going to behave in a similar way. And so the only thing that we're differing in these functions is this one number here. So that a, it could take on the value 1, or it could take on -1, or it could be -1,000,000, or 12, or pi, or some number. But what we're claiming is that all of these functions are going to behave in a similar manner. And so what we want to do, instead of studying each function individually, we put in a parameter here, and we're going to study all the functions simultaneously. So the students that are here live have been thinking about this for a moment. So everybody that is here, do you need another minute to think about this, or are we good to talk about it? All right, so let's go ahead and put our definition or our question up here in the top left, and we'll start to walk through this. Okay, so what we're going to need to do is we need to find some information, right? So we're asked for critical points, we're asked for inflection points, and then we're asked for some local max and min. So what we'll do is we'll use this also as a reminder for all the different tests for local max and min, right? Notably the first and second derivative test, but also sort of what is a critical point, an inflection point, and so on. So for the first part here, if we're going to find a critical point, what we need to know is we're asking this question, hey, when is f prime of x equal to 0 or undefined, right? So this is what we want to know. Okay, so where is our derivative? We're going to take our derivative when we ask that question. Where is it 0? Where is it undefined? Okay, so in this particular context, our derivative here is a plus 2x. Okay, now this is a polynomial, right? It's a quadratic function. Derivative is always going to exist, and we can see that through the formula, right? There's no time that I'm going to get anything outside of the domain, right? So things like taking the square root or of a negative number, dividing by 0. There's no weird trig functions in here. So this will always be defined, and it's going to be 0 when, right, so we would set this a plus 2x equals 0, and x is going to be equal to -a/2. Okay, so far so good? All right, so one thing to point out here, at -a/2, you're not getting a number, right? So this isn't a number in the traditional sense, but for this problem, we're thinking about a as a fixed value, right? So our variable in our function is x, so that's where you would plug in your inputs that you would find points with, but a is going to be a fixed number, okay? It's a fixed parameter in relation to this problem. So this is going to be a particular point on our graph, just depending on what family we have, right? If a is 10, then we would look at this value, we'd have -10/2, which would be -5, right? So if I have that value for a, I can go ahead and find my critical value, but it's just going to depend on this number a right here, okay? All right, so this is our only critical point. It's the only place where the derivative is 0. And for part 2, what we want to do is we want to go ahead and we want to find our inflection point, or our inflection points, okay? So for our inflection points, what we would do is we would take the second derivative, okay? So the second derivative to this function is, right, so if we look at this, I take the derivative. A is a constant, so it goes to 0. And then when I take the derivative of this, it's just 2. Okay, so So I asked myself, my inflection points, right? That's going to be where the graph changes concavity. So the second derivative goes from positive to negative or negative to positive, but it's always positive, right? So this thing never changes. There's no place where this is going to go from positive to negative. It's always positive. Okay, so what this tells me is, hey, my derivative here, right? My second derivative is always positive, so my graph is always concave up, right? Right. So our graph here is always concave up, so there's no inflection points in this one, right? So it's never going to change concavity. Okay, so a couple pieces of information. We have our critical point here. We know the graph is always concave up. And now what we want to do is we want to go and figure out what our local max and min values are. So we'll do that down here. Okay. And so what we need to do a couple things. So we could use the first derivative test, right? Or we could use the second derivative test. There's two ways to tell if we have local max or min. We're going to go through, we're going to check all of our critical points, right? So we only have one to check. And then the question is, hey, if my second derivative is non-zero at that point, and depending on the concavity of my graph, right, we can tell if we have a local max or min. So to do that one first, right, so we're always concave up, which means our graph looks like this. And so at our critical point, we're going to have, right, our second derivative test says this is going to be a local min. Bye. My daughter in the background there. She's fine. She's over there. All right, so we have a local min at this point. Alternatively, what we could do is we can create a sign chart, right? So we have this value, negative a over 2. And what we want to do is we want to check that, hey, if I plug in values that are bigger or smaller than this, what happens to my... Here, can you take that book and sit down, please? Zoe, why don't you read this book? No? Okay. All right, so sorry about the interruption, but all right, so I have this value negative a over 2, and what I would like to do is check, hey, on either side of this, and I should verify that it's increasing or decreasing, right? And that means my first derivative is either positive or negative at that point. So if I plug in a value that's bigger than negative a over 2, right? So could be anything, right? So anything to the right of this, right? So if I have something over here, maybe negative a over 2 plus 1, right? So if I were to plug that in to my function, what I'm going to see is, right? So let's go ahead and do that. Right, let's plug in negative a over 2 plus 1, and we'll go back, right? So what is f prime of negative a over 2 plus 1? Right, so this is a plus 2 times negative a over 2 plus 1. You get a plus negative a plus 2, right? And so that equals 2, which is going to be a positive number, right? So if I pick something to the right of negative a over 2, I'm going to get a positive number. Similarly, if I pick something to the left of negative a over 2, I'm going to get a negative number. And so my first derivative test should show me something like this, right? So we're decreasing into that point negative a over 2, and we're increasing out of that point negative a over 2. Okay, so with all of this analysis right here, I have a pretty good understanding of this family of functions, right? So it's going to be always concave up. It's going to look like a parabola, right? So based on its formula, right here, it's going to achieve this local minimum value at negative a over 2. And so we can go ahead and then let's use our graphing utility to sort of make sense of all this. Okay, so here's all of our analysis, and then we'll go ahead and use Desmos to figure this out, all right, to see how this extends. All right, so can you all see this? I think you can see this, yeah. All right, so here's our function ax plus x squared, right? We see it's a parabola, and as I am gonna drag this, correct, so there's no local max to this function. Yeah, so we had a question, there's no a local max. But so if we look at it, right, it looks like a parabola, and then if I drag a, right, so if I change the value for a, we can see that the function is always concave up, and it has this point right here, right? This is our local max or our local min. So what we want to verify now is that, you know, that point, right, no matter where it is, I always want to verify that this point right here is negative a over 2. Right, so I can graph this point negative a over 2, comma, f of negative a over 2. Right, so this, I got this point right here from my analysis, right, what we did on the chalkboard. And we can see that no matter what my a value is, that's always, right, this point right here is always my local minimum value, no matter what this parameter a is. Okay, so throughout this whole thing, we always get this minimum value at negative a over 2. Okay, so this is going to be important. What we're going to do is we're going to look at functions that have parameters in them and see how we can use them to model different things. Okay, so one of the activities today is we're going to see a logistic function, right? And we're going to see how we can use that logistic function to model. That's the exact function that they use to model the disease spread in a population that we're seeing right now. Okay, but this is a warm-up example to see this function. So I want to pause here and kick it over to you all, see if there's any questions about this one. Feel pretty good? Yeah, all right. Okay, so what I want to do now is let's go over to our book, right? So as we see here, this is activity 3.2.2. It's a similar one to what we just did, okay? So except I'm going to give you a new function, ax, or x cubed minus ax. So similar polynomial, not a quadratic anymore, but a cubic. And we want to walk through the same behavior, right? We want to find the critical numbers. We want to do the sign charts, right? Second derivative, find the inflection points, and then we're going to try to study the behavior, and just like I did on the chalkboard, okay? Similarly, we could then go and graph this on Desmos, okay? And then you'll have a slider A, and you could see the different values of the function, right, where it is. But in order to precisely pinpoint those local maxes and mins, we want to do that analysis out by hand or on a rate in general, because it's numerically it would be hard to find those maxes and mins without sort of knowing what all the values are. So we've got 4 people here. I think this is probably a good opportunity. I'm going to I'll drop us into breakout rooms, so I'll split you off 2 and 2. And then we can take a few minutes, right? So you'll have a partner here to think through this activity 3.2.2. I'll jump back and forth between the 2 rooms, and then we'll come back together and see what we figured out. Okay. Let's see here. All right, so we should see them opened now.
of x is equal to 0, right?
Yeah.
Hello?
Should be easy enough. What's up?
How you guys doing?
Good. Just
Good.
finding a critical point.
Gotcha. You're already on your way. So does this process feel
Yeah.
pretty good for you?
Yeah, it's pretty good. It's easy enough.
Yeah.
Even with the
not bad.
parameters in there when we have like the letters for values.
Yeah.
Okay. So if that feels pretty good, this can be some of the more challenging stuff that we come across. Just to keep in mind that we have these parameters and we have variables that are happening at the same time.
Yeah.
Okay, but you all feel pretty good about it?
Yep.
I'll jump over to the other room. See how they're doing. Hello. So we're both muted here. So how's this going? Did we follow that process pretty well on the with the warm-up example? We sort of know how to tackle this problem.
For the second part, like the inflection points, how do you know if it's concave up or concave down?
So you're going to take the second derivative, and then you're going to test where the second derivative is 0. Right, so you're just like we found critical points for the first derivative. What we're going to do is we're going to find where the second derivative is 0, and then we're going to test on either side of those. Hey, does it go from increasing to decreasing, or positive to negative in the second derivative? So if the second derivative goes from positive to negative, then you're going to have this being concave up. Sorry. Let me think about this for a second. So second derivative, you want to know where it changes concavity. So that's right. So if it goes from positive to negative, you're going to change from concave up to concave down. Right, so let me share my screen here. So x cubed plus ax. All right. Bye. You doing okay? Yeah. Okay. Can Daddy finish doing this over here?
Zoe, come here.
No.
Come see Mommy.
Here, come here. Sit with Daddy. Ready? Daddy's gonna write on this. Okay, so what we're gonna do? No, it's Daddy's turn to do it. Right, so you'd get 3x squared plus a. Right, so this would be our first derivative, and then we would go ahead and take our second derivative, and we would get 6x. Is this good so far? Okay.
Yeah.
So for the second derivative, yeah, we're talking to people, right? So these are my students over here. Up there, see? They're right up there. We're talking to them on the computer. You want to play iPad games with Mama? Okay, so just the same as we did with the first derivative sign chart, we would look at our second derivative sign chart and ask, when is this 0, right? So when does f prime equal 0? And so the only time that's going to happen is at this point 0, right? So we're going to check to the left and to the right of it. And so I put this f double prime over here on the left, just for my own sake to look at this and say, hey, yeah, I'm looking at the second derivative now. And so I can pick values right to the left and to the right of this and plug them back in to f double prime. So I'm looking at values like f double prime of -1 and f double prime of positive 1. And so what I would find is that over here it's negative, and then over here it's positive, right? So what this would tell me is, hey, this function is concave down, right? So to the left of 0 for negative values, I should see that it's concave down. And over here, I should see that it's concave up. Right, and so what that means is that at 0, I have this inflection point. Right, so this is going to be a point where we should see when we look at the graph that to the left, right, so when it's negative, you should see concave down, and to the right, when it's positive, you should see that it's concave up. So does this help answer your question?
Yeah, that makes sense. Thank you.
You're welcome. Yeah, I messed up the function now. I think it doesn't matter for the second derivative, but yeah, with everything that was going on over here. This should be a minus, right? So just to correct everything here, right? So this, we didn't do anything with the first derivative where it mattered, but this would be a minus a, right? So. All right, so how are the other questions? You got up through ABC.
Everything else is good.
All right, so we feel pretty good about this one. All right, so let's go. I'll jump back to the other breakout room, and then I'll probably bring us all back together here in just like in 1 minute.
Where the middle of the graph goes through.
All right, excellent. All right, so y'all feel pretty good about this?
Yeah, we were
Yeah.
wondering, like, so when we get the inflection point, is that just, what does that do for us? Or at least
It
that's
tells-
what I was wondering.
It tells you where it changes concavity, right? So where it goes from concave down to concave up.
Yeah. Wouldn't
So,
there
right.
be multiple of those?
No, there's only one in this case.
Oh, okay.
So is
yeah,
it
I see.
not? So is it neither a max or a min?
So there's a local. There's not any global maxes or mins, but there's local ones,
Yeah.
right? So this point is a max, right?
Oh, I plugged the run value into the number line.
Yeah, this
Yeah.
would be a min, and then this is going to be your inflection point right here. All right, so I guess the question that we'll have is what are these values?
Is that just
You get those from plugging in from plugging in your critical point into, like, you do it the critical point +1 and -1, like we
You
did the
could,
last
yeah.
question.
Mm-hmm. But what are these values though? Like, could you find this point on the graph?
Oh, you want me to look at it?
Yeah. So we'll come back together. So the other group is pretty much done with this one too. So we'll go ahead and we'll go back. I'm gonna close the breakout rooms, and then we can all talk together. All right, so we're just missing Emily here. Okay, so let's go ahead and take a look at our function, right? So it was f of x equals x cubed minus ax. We had a slider a. Okay, so let me share. right, so we were looking at this family of functions, right? So when A is positive, when A is negative. And so in one of the breakout rooms, we were asking the question, you know, how do we find these points right here? So Lou, Caleb, we were talking about this, right? So could I find a formula that tells me where this point is and where this point is? So Sophia, Emily, did you figure that out? What a formula for this local max and this local min is when A is positive? Did anybody find a formula for it? You don't know it, yeah. Okay, so let's go ahead and flip back over to our Blackboard here. There we go. Okay, so we've got this function, right? So we've got f of x equals x cubed minus ax. And then when we take the derivative, we're going to get 3x squared minus a, okay? And the question is, when is this 0 or undefined? And so it's never going to be undefined, right? So it's a polynomial. The domain is all real numbers. But when I set this equal to 0, I would get x squared equals a over 3, or x is equal to plus or minus the square root of a over 3, okay? And so through looking at a first derivative sign chart or the second derivative test, you know, we could check these things, right? So one thing we want to notice is, hey, a is always positive, because if it's negative, then this is going to be undefined, right? So we're only going to get these values here. They're only going to exist when a is a positive number. If a is a negative number, we'll have issues, right? So let's keep this in mind, plus or minus square root of a over 3 when we go back to our graph. Okay, so we've got our graph here, and then so we want to find some values on our graph, right? Negative square root of a over 3, right? We want to check this value. So this is going to be our input, and then we're going to check, you know, the same value as our output, right? So this, the negative square root is popping up as our local max, and then if I look at the positive square root, that's going to be our local min. Okay, so no matter what, right? So no matter what the value for a, this point right here is always our local max, and this point down here is always our local min. Now, when this goes negative, what we should notice is, hey, these things come together, right? So as I get closer to 0, well, now they don't exist anymore, right? So they're not existing. We don't have any local maxes or mins when we're negative, right? So our function is always increasing, it looks like, right? So we get sort of something a little bit different when a is negative, and then when a is positive, we see that we do get these two local max and min values. Yeah, you do need a, right? So in any time that you're going to be looking at these families of functions, the values you're not going to get, right? You're not going to get explicit numbers for these max and mins. You're going to get formulas for how to find them. Yeah, so a lot of the time, I wouldn't want to say it always depends on the parameter. There are cases where you have a parameter and it doesn't depend on it, right? So in this case, we saw that our inflection point is 0, no matter what the value for a is, right? So a is not affecting our inflection point, but it is affecting our local max and min value. So sometimes parameters can affect one part of the graph, maxes and mins, while not affecting another part, the inflection point. Okay. All right, so to take the next step here, right, we've seen two examples where we can study families of functions. So we are about to kick it up about a few notches, all right? So we're gonna go ahead and look at a new function down here, activity 3.2.4, which is the logistic function. Okay, so the logistic function has this form: L of t is a divided by 1 plus c e to the minus kt. So yeah, Luke, so to answer your question, it's not, right? So to go back, so Luke asked the question, is the local max and min not a set number? Yeah, it does, it's not, right? So it's not always going to be the same number, right? So it depends on A, right? So I can always tell you where it is, right? So the local max will always occur at the input negative square root of A over 3. But in order to tell you exactly where that is, you're going to have to tell me what this A value has to be. Okay, so I know that the family behaves all in the same way, but you need to tell me, right, what parameters do I plug in order to figure out the precise values. Does that clarify what's going on here? So it's not going to be a fixed number. Right? It is fixed in the sense of a parameter, right? So it's always going to be this, but depending on what A is, this will change. Right? Okay. So let's go over here, and we're gonna take a look at this last example where we have a logistic function. Right? So as I read it off before, right, we're gonna have three parameter function here. So we have a value A, we have a value C, and then we have a value K. Right? So those are all parameters. Our variable in this case, our input is going to be T. Okay, so this T right here is going to be our input, and then E is just is a number, right? 2.7182. Right, so that is a fixed number that we do know. Right, so that's E. Okay, so we're gonna look at this family of functions, and then we're gonna work through these questions and see if we can figure out sort of what this function does. All right. So part A, right? So what we want to do is we're going to look at this function, and we are going to write it as they suggest here. Okay, so we're going to write it as L of t is equal to A times 1 plus C e to the minus kt to the negative 1 power. Okay, so we're going to take the derivative, and we're going to look and see why does it have no critical numbers, and try to determine where it's always increasing or decreasing. Okay, so if it has no critical numbers, right, then the derivative is never going to be 0. It's never going to be undefined. So we'll always be positive or always be negative. Okay, so here's our function. What we want to do is take this derivative. So remember that A, C, and K are numbers. So we're going to treat them like constants. And then the only time that we have a variable is this T right here, which is in this exponent. Okay. So we're going to take L prime of T. And so our A is a constant, so that gets to come down for free. And then what we're going to do is we're going to use power rule and chain rule on this piece. Right, so we're going to get negative 1. Right, we'll bring that down. We're using power rule here. We're going to leave our inside alone, 1 plus C e to the minus kt. And we're going to multiply this by the derivative of our inside function. Right, so I'm going to multiply by the derivative of this. And so when I'm going through taking the derivative of 1 is 0, so that goes away. Then I have the derivative of c e to the kt. So this is going to be c, then we're going to have e to the minus kt, right? So this is going to be the derivative of e to the t, and then I have to multiply by the derivative of that inside function, which is negative k. Okay. So let's bring all of this together and look at it in a cleaned up way. Okay, so as I break this down, this right here, this is going to go into my denominator since it has a negative exponent, right? So I'm going to write this as 1 plus ce to the minus kt squared. And then in my numerator, we are going to get, we'll have an a, right? So a comes down, okay, and let's group some other things together. So I'm going to get a c, a minus k, and a negative 1, right? So that becomes ck, right? So you get ck, and then e to the minus kt. All right, so this is going to be my derivative, and the question is, what are the critical points, right? So when is this thing equal to 0, and when is this thing undefined? All right, so our conditions here are a, c, and k are positive real numbers. Okay, so a, c, and k are positive real numbers. So when could this thing be 0, and when could it be undefined? Right, so when I look at this, when it would be undefined is whenever, say, the denominator is 0. Right, but if I look at this function, what I have on the inside is I have this exponential. Okay, so this is going to be an exponential function. So this is it's never going to be 0, and it's never going to be negative. Okay, so this will always be some positive number. And I'm adding 1, right? So I have a positive number times a positive number plus 1. So this denominator is always going to be positive, and then I square it, right? So that's positive. So this denominator is never 0. It'll never ever be 0. So this is never undefined. And then I ask myself, same thing, is my numerator ever going to be 0? Well, a, c, and k are positive, so they're never 0. And this is an exponential function, which is never 0. And so what we have here is that this is never 0, right? So it's never 0, it's never undefined, so there are no critical numbers. And then the question is, well, is it positive or is it negative? Well, looking at the denominator, we've got something squared, so the denominator is always positive. A, c, and k are always positive, and this exponential function over here is always positive. So every term in here is positive. So what that means is that this thing is always greater than 0. And so my function is increasing, right? So what we should see is that this function right here is always increasing, right? So no matter what happens, this thing is always increasing. Right? So no matter what value for t, as we move from left to right, as t increases, our outputs will always go up. All right, so let's jump back and let's see, right, let's see our next question here. So our next question says, given the fact that our second derivative is this mess, right, so the book is giving us this second derivative. We don't have to take this. They're telling us this is what the second derivative looks like. We want to know when this function is concave up and when it is concave down, right? So when is it concave up? When is it concave down? So when we look at this, so I'm gonna jump over to the Blackboard here in a second, but I want to know when is this equal to 0. So using the same ideas that we did before, I'm going to just sort of check what could make this thing 0. Well, I'm not going to get a 0 by dividing by anything, and then As we said, A, C, and K these are all positive numbers, and then this exponential function right here is positive. So maybe this term right here, C e to the minus kt minus 1, the only time my second derivative is going to be 0 is when we have, right, so is when we have this right here, C e to the minus kt minus 1, when that thing is equal to 0. Okay, so let's jump back over and look at our Blackboard and see if we can figure out, hey, where that function is equal to 0. Okay, so we have this C e to the minus kt minus 1 is equal to 0. So C e to the minus kt is equal to 1, or e to the minus kt is equal to 1 over c. So then what we can do is take the natural log of both sides. So you get minus kt is equal to the natural log of 1 over c. And so t is negative 1 over k, natural log of 1 over c. Right, so this is going to be our inflection point. Okay, so what we're going to do is take a look at this and say, okay, so in this logistic growth model, the inflection point should be right at this point, negative 1 over k, natural log of 1 over c. Okay. So we know that our function is always increasing and it changes concavity at this particular point. And so the last thing that we want to do is look at the limits, right? What happens as time goes to infinity or time goes to negative infinity for these things? And so the one that we're going to be most interested in is when time goes off to infinity. So really quickly, I think it's going to be clearer with a graph, but as t goes off to infinity, this term right here is going to end up going to 0. So you're going to have an exponential function, right? So since this negative k, right, so this exponent is negative, when t gets really, really big, this term's going to get really small. So we should see it just gets really close to a. Okay, so let's go over to our Desmos graph here, where I already plugged in our function here, a over 1 plus c e to the minus kt, and then we can play with some parameters here, right? So you can see that as I move these around, right, we can see different shapes happening. Right? So a couple things that we want to notice. This point right here, right? So see how as t gets really, really big, as our inputs get really big, this graph starts to flatten, right? So we get this flat point over here. And so the value there is y equals a, right? So what we do, this is called our carrying capacity, right? Or this is going to be the point where, you know, a population stops growing, right? So no more new population here, right? So you can think about lots of population models in this sense. So no matter what a is, right? So that's going to be our carrying capacity. So we can make this bigger. Right? Okay, so we could have, no matter what a is, that's going to be our carrying capacity. Now, the other value that we found was this negative 1 over k, natural log of 1 over c, okay? So we had this value right here, and then I want to look at my function L evaluated at that point, okay? And so what we did on the chalkboard, we found that this was our inflection point, right? So no matter where we are, right, no matter what my parameters are, I see that my function's always increasing, and right, we have this inflection point right here. Okay. So what I want to point out here is this is how we model population growth, right? We see this typical S curve, which is a logistic curve. And so what I did is I took our COVID-19 data, right? So I looked at all the cases in the US, and I've plotted them on this graph, okay? So if we look at just the number of cases each day plotted over time, so March 10th, right? So my time 0 here, it says on March 10th, we had 754 COVID-19 cases in the US. And then each day, right, this is a new data point, right? So 1 month after March 10th, we had 432,000 cases. And then as of today, we have 825,000 cases, right? So what we're seeing here is we have a graph that looks pretty similar, right? So if you think about these two shapes right here, this is the logistical growth curve, right? So depending on where we are in the curve, right, people talk about when is the growth starting to slow down. So if people are very, very interested in this point right here, right? So if we think about this, what we're going to see over time, so let's put in another slider here. Okay, so what we're going to see grow over time is we're going to have a function that grows something like this. Okay, so we want to know, we want to figure out where are we in this curve, right? So where are we in the logistical growth curve? We look something like this right now, and what we're hoping to see is if we hit that inflection point, then that's where we're going to see growth start to slow down, and then we'll eventually reach some sort of final state, right, where we've had the maximum number of infections and then no new people are becoming infected at that point in time, right? So right now, we seem to be somewhere in here, right, if you look at our COVID-19 data. So really what we want to start to see is we're hoping that this curve starts to flatten out and we start to see infections start to go down. So if you've taken statistics, one of the statistical tools that you can use is called a regression. You can do regression on your data. And you can see that this logistic function, right, it fits this data pretty well, right? So if I do a logistical regression, we get this logistic growth curve, right? So right now, this would be sort of the prediction for how things are growing. But you can see lately, especially the last 2-3 days, we're already above that, best fit curve. So we have a hard time right now actually telling us what those parameters are, right? So so these are parameters that I put in for the logistic growth function. But so our A would be this right here. So best case scenario is that we would have a carrying capacity about 900,000, but I don't think that is going to be very accurate, right? So what we're seeing here is, right, if you track the number of new cases each day, it's pretty level. Right? So we're seeing about these 30,000 new cases a day. So we'll see how things grow, but just a calculus example of how people are trying to model what's happening, the uncertainty around parameters, right? And so depending on what parameter you choose, right? So what your parameters are, we don't necessarily know exactly where this is going to be, right? So we don't know exactly what the carrying capacity is, or what our growth rates are going to be, how steep it's going to be, or how quickly it's going to level off, right? So we know that it's going to grow something like this, but we don't know the exact values of these parameters. But this is a way that, right, we're seeing calculus being applied very explicitly to modeling our current situation, right? So we can see that these families of functions are what we're working with right now. So I'm past over here, but this was pretty complicated. So I'm glad we got it on video so you can go back and sort of take a look. But I'm going to kick it back over to you all and see, is there anything I can clarify or questions I can answer? All right, so I'm going to call it here. And so we'll come back on Friday. And what we're going to do is we're going to jump into section 3.3, where we start to do some optimization, right? We're going to look for things that are local maxes, local mins, and then we're going to start to think about global maxes and mins as well. Right, so you too, I hope you have a great day. I'll see you all on Friday.